Pasha bhai.
Assalamualaikum, Professor.
Your partner?
I'm waiting for them.
No need. Because it's already 11. You follow the class timetable. Where's Ibrahim? Ibrahim?
Professor Ibrahim is not in our group.
Ibrahim?
He's not in our group. It's Rashad and Akil.
Okay, Rashad. Oh, Rashad, no. Rashad? Call Rashad.
Professor, they are on the way.
Be quick.
Assalamualaikum, doctor. Actually,
Okay. On your video. Okay.
Doctor, can I get 1 minute because my PC is installing the Zoom. My PC didn't have the Zoom. So can I get 1 minute? Please?
8 minutes. Be quick.
Okay, thank you, doctor.
Pasha says share the slide. Pasha bhai.
Yes, Professor. Give me 1 minute. Professor, I'm not sure how to share from the iPad. There's no option to share from Google Sheets and Google Slide.
Use laptop. Use laptop. Okay,
No, it's not it.
who's going to share? You.
Doctor, we were supposed to share the questions that we are individually gonna present. Oh, I found the option, Doctor. Can you see my screen, Professor?
Okay.
So this is our group, and Rishad is going to present the first two. Akil is gonna present the second, the following ones, and I'm going to present the last one, 10.10. So we will begin with Rishad.
Can you move my picture to the left or to the right? Or close it? Okay. Bismillah. Okay, Baisap.
So now we will wait for Rishad to present the first two.
Rashad Bhai.
Actually, my PC crashed again. So, doctor, can I present from
Yeah.
science?
Yeah, sure.
Okay. So, Assalamu alaikum, doctor. We are from group 19, and our task was assignment 6. So
Video.
this is our first question. So here we are given a feedback control system, a transfer function, and we need to verify that the gain margin is infinity and the phase margin is 9.8 degree. So we know that for calculating the phase margin of the system, we need to know that the gain crossover frequency is equal to 1. I mean the magnitude of the gain system, magnitude of the gain of the system is equal to 1. So we replace the transfer function on S with j omega. So here the first line and the second line is the phase margin equation, minus tan inverse to 2 omega divided by 15 minus omega square. And in the next line, we calculate the value for j omega, and we put the magnitude is equal to 1. And from that equation, we calculate the value of omega, and the value of omega is 12.8 rad per second. And by putting the value to the phase margin equation, we get the phase margin is equal to 9.8. And the same thing for the phase margin equation, we put the angle value is equal to minus 180 degree as per our condition said. And by solving this equation, we get the omega value is equal to infinity. So from that manual calculation, we proved that the phase margin is equal to 9.8 degree and the gain margin is infinite. So can you move to the next slide, the MATLAB source code? Okay, so the MATLAB source code, first we set the value for the gain by using the k variable, and next we use the transfer function, the TF function to define our transfer function, and then we use margin function to generate the gain margin and phase margin value, and we print it here as you can see in the graph. Can you move to the next slide, the graph? Yeah, so we can see the graph here in the phase margin graph. We can see at the as we calculated our omega from the manual calculation, our omega was second, and in the graph at the omega 12.8 rad per second, our phase margin is 9.8. And for the magnitude, the magnitude supposed to be infinity, but for the plot purpose, we set a large value for the gain margin. It's only for the visual representation. So now can you move to the next slide? Yeah. So for the second question, again a transfer function given, and for t is equal to 0.2 second, we need to calculate the k value, and here another condition given: the phase margin is greater than or equal to 45 degree, and also we need to plot a graph for time versus phase margin. Also, they're given a condition. So can you move to the manual solution? Yeah. So here we replace our transfer functions s with j omega, and then from that we calculated the magnitude, and we from that equation we got one equation: k is equal to root over omega square plus 100, and by using the phase margin equation we got another equation: minus j omega t minus tan inverse 0.1 omega gc, which is gain crossover frequency. So as we have the value t is equal to 0.2 second, we just put the value here, and for the phase margin, as we given the phase margin is greater than or equal to 45. So from that equation we also got the crossover frequency for phase margin, which is minus 2.356 rad per second. So we got two equation, and by solving these two equation we also got another omega, previous one that was the phase margin, and the last one is our omega. So by using those values we get the value for k is equal to 13.15. And for the second part also, we from the first part we got the equation for the phase margin, and we just put the value here, and by using this value we made a graph. Zahin bhai, can you show the excel graph? No, not this one is the excel graph, but the main excel file.
Oh, wait, the one you sent on WhatsApp?
Yes.
Can you send it to me again, because I don't have it on my...
Okay, I'm sending it to you.
No need, proceed.
Okay. So by using the values for by using this equation we written here in B, we plot this graph. The graph initially starts from time 0 and phase minus 40.5, and it ends at time 0.3 and the phase value 106.3 degree. So can you move to the MATLAB? Okay, so for the MATLAB, the provided code which is used to calculate the gain and phase margin for the given transfer function. So here we set our we define our transfer function by using the GS parameter, and we also initialize our values by using WGC and FLWGC, and in the while loop we increase the value by 0.1 and recalculates the transfer function g of s using the updated k and WGC. Also, it calculates the phase margin in degree based on the shift at WGC. And after the loop, the code plots the both plot by using the function GC, GS, and also the margin function. It includes the gain margin and phase margin line in the plot, and then finally the code displays the calculated value of the gain that results in a phase margin of at least 45 degrees. So we can observe that the phase versus time. Here we can see the our observation is like in the phase versus time graph, we skews at different places. So I'm passing the next slide to my brother Akhil to present.
Assalamu alaikum, Doctor. Apologies that I couldn't join from my laptop. I just finished my lab, so sorry about that. So for the next question is, it says that consider a unity feedback system with the loop transfer function LS equal the equation where Z is 1 and P is 3.6. The actual percent overshoot for the compensated system will be 46%. We want to reduce the overshoot by 32%. So using an M file script, determine an appropriate value for the zero of GCS. So for the manual solution, we have that to reduce the overshoot percent to 32%, we can use the formula of the damping ratio, which is percent overshoot equal 100 times e to the power minus zeta times pi over 1 over pi over root 1 minus zeta square. So solving this equation for the zeta, we can get the value of zeta using the percent overshoot of 32. So we get the zeta value of 0.5. Moving on for the second step, we need to write the characteristic equation, which is 1 plus GCS times GS equals 0. So it's just a shortcut, or directly we are getting to the characteristic equation instead of using all of those calculations. So we know what is GCS and GS. So by replacing them, we get the equation, which is the final equation we get is S square plus S plus 3.6S, S square plus 4.6S plus 11.7 equals 0. So this is the simplified equation for our characteristic equation. So in the next slide, we can see that in the quadratic equation, we have S, we can solve this characteristic equation using the quadratic equation solution. So for S, we can use this formula, and by using the calculator, we get two values for S1 and S2, which is minus 2.771 and minus 2.829. So we can replace the S1 and S2 values in GCS. So from the so after plotting the value of S and Z and P, we get GCS. We get two values for GCS, which is negative 0.386 and negative 0.408. So these are the values of the GCS1 and S2 are approximately negative 0.386 and negative 0.408 respectively when Z is 1 and P equal 3.6. So moving on to the MATLAB source code, we first give the parameters of Z equal 1 and P equal 3.6, and also what we want our desired percent overshoot to be. And moving on is we use the formulas given in the manual calculation. Just use these formulas to calculate the zeta and omega n. And also we can calculate the desired pole using this formula given in the source code. So we just simplified all of the formulas, and after calculating the value for poles and zeros of GC, we use the transfer function, TF function, and replace the values of Z desired and pole desired. So after that, we calculate the margin for gain margin and phase margin and omega GM and omega PM, which is gain crossover frequency and phase crossover frequencies, and we plot the graph. For plotting the graph, we will plot L or GCS times GS whole together, not just the GCS. So moving on to the next MATLAB output is the approximate value we get from the MATLAB is negative 0.6971. I hope that's acceptable. And as for the gain margin and phase margin, we have the outputs as gain margin is 14.26 decibel and phase margin is negative 34.61 degrees. For gain margin, we get the gain crossover frequency at 0 radian per second. And for phase crossover frequency, we get 1.82 radian per second. So moving on to our next question. Consider a circuit with the transfer function GS equal, the equation is given, and where we have we have a capacitor and hello.
Yes, we can hear you.
Oh, sorry. So for this equation, so the equation is given, and we have a circuit for the transfer function, which is capacitor and and
Busy.
Resistance.
resistance. Sorry, thank you. And the resistance. So we need to plot the frequency response. So moving on to the manual solution. So we just need to plot the GS and nothing else. So it's simple enough. We just replace the value of C and R in the equation, and then we can substitute the S in S with J omega given in the equation, and then we use the magnitude value. Then we get the magnitude and the phase angle. So for the corner frequency of omega C1 and omega C2 are 100 radian per second and 1000 radian per second. We will use these magnitudes, and by using the the magnitude equation, we can get the solution for omega up from 10 up to 5000. That's the range of omega we can calculate. So for the next slide, we have the magnitude and rate and the frequency response and the phase and the frequency response. So for the magnitude, we start from 0 and go up to 5000. It keeps on moving up, or it keeps increasing, but after that it stabilizes. And yeah, that's the value for the magnitude. And for phase, that's the curve. The peak frequency is around 50 degrees. The peak phase is around 50 degrees. Sorry. Moving on is the MATLAB source code. So for the MATLAB source code, we just need to plot. So we refine the capacitor and resistor values as C1, C2, R1, R2, and then we just use the numerator and denominator coefficients and use the transfer function TF and place the transfer function as G equal TF and numerator and denominator. So then we just plot with both G and then turn on the grid, and then we fix the titles and so on. So this is the MATLAB output, where we get the gain margin as infinity and the phase margin as negative 95.74 degrees. And gain crossover frequency is non-existent, and the frequency for phase crossover frequency is very small, so we consider it as 0. So that's all from me. Now I will pass it to my brother Zahin Bhai.
Thank you, Akil Bhai. This is Sahin, and I worked with the assignment 10.10. So the question goes, consider the feedback control system shown in figure 10.10. The time delay is t equals to 0.2 second. Plot the phase margin for the system versus the gain in the range 0.1 to 10. Determine the K that maximizes the phase margin. So in a manual solution, what we did is the transfer function of the system is given, and then we replace S with J omega. And when we replace it, we separate the magnitude and the phase of the loop transfer function. And then to find the K that maximizes the phase margin, we need to plot the phase and gain margin for the values 0.1 to 10. So Professor, would you like to see the Excel file?
Just browse through. Okay, be quick.
All right.
Just follow the slide. Just follow the slide.
All right. So this is the magnitude and frequency curve, and this is the phase and frequency curve. So let me explain the MATLAB code.
Why
The code begins.
Why the phase is -1, -2, -3? It's supposed to be in degrees. I think all your Excel file is wrong because the magnitude should be decibel versus frequency, and phase is degree versus frequency. Who plot this?
Was it Akil?
I don't know. You better check again, and then
Yeah, Doctor, I plot this one. Maybe I
it's
made a
wrong.
mistake.
It's wrong. All your Excel is wrong. It's supposed to be magnitude in decibel versus frequency and degree versus frequency.
Yeah, yes, Doctor. Maybe I made a mistake.
You take note of that.
Let me explain the MATLAB source code. The code begins with defining a range of values for the gain k in the variable k values. It starts from 0.1 and increases by 0.1 and goes up to 10. Two variables, max phase margin and optimal gain, are initialized to store the maximum phase margins found so far and the corresponding optimal gain. The code enters a loop that iterates over each in the k value array. Within the loop, the current value of k is assigned to the variable k for calculation. The time delay Ts, numerator coefficient num, and the denominator coefficients den of the transfer function are also defined. The transfer function g is created using the numerator and the denominator coefficients along with the specific time delay.
Next.
The feedback. I will move on to the output, or do I keep explaining the code?
Next.
All right. The feedback transfer function h is set to 1, representing unity feedback. The closed loop transfer function t is calculated by applying feedback to the transfer function g with the feedback transfer function h. The code checks the stability of the closed loop system by analyzing its step response. If the step response does not contain any nan, that is not a number of values, the stability analysis proceeds. The phase margin is calculated by generating the Bode plot of the closed loop system and extracting the magnitude and phase values. Then the current phase margin is determined by finding the maximum phase value and subtracting -180 degree. The current phase margin is greater than the maximum phase margin found so far. The max phase margin and the optimal gain variables are updated accordingly. After iterating over all the k values, the code has found the optimal gain value maximizes the phase margin. The Bode plot is then generated after transfer function with the optimal gain value, allowing visualization of the system's frequency response, which we can see in the output. The Bode plot is then generated for the transfer function with the optimal gain value, allowing the visualization of the system's frequency response. Display settings are adjusted to show the magnitude in decibels and the phase in degrees. Finally, the optimal gain value and its corresponding phase margin are displayed using printf statements.
Okay. Finish.
Yes, Professor.
Okay, take my note there. Your all Excel file is wrong. Replot again. Magnitude in decibel, degree versus frequency. I don't see any flowchart in your assignment. You show the program, but no flowchart. And then no Simulink. I don't see any Simulink file here. So I'll give you 1 week to repair your slide and submit by this Saturday.
Thank you, Professor, for the
Thank you,
extension.
Doctor.
This Saturday.
Thank you, Professor. Thank you.
Rest is wrong, so you have to take note. Rashad, what is the comment?
Yes, Doctor.
What is the comment? My comment.
Your comment.
What
You
should
know very well.
Number 1, all Excel file is wrong. Redo again. Number 2,
Yes, Doctor.
no flowchart in the report.
And
Slide.
number 3 is Simulink.
No Simulink. Your Excel file all is wrong. So you have to repair again. The
Yes, doctor, my annotation is wrong.
your assignment is failed lah, because information is wrong. Okay, you may exit
Okay,
now.
doctor, we'll fix. Okay, okay.
Let the brothers enter.
Thank you, Professor.
Thank you. Assalamualaikum.
Assalam.
Okay, Mamdo, get in. Muhammad Mamdo. Osama Mamun.
Yes, doctor.
Chia Kawi, wait, we have the time delay because Asha, you can go out. Asha, leave meeting.
I don't know where is Osama. I WhatsApped him, but he's not responding.
Asha, leave meeting because other people want to share.
So doctor currently is group 18 or group 17?
You wait, Chia. I will call you.
Okay, okay,
Because this Bangladesh group has a lot of time delay.
okay.
Pasha, bye. Leave meeting. Okay, Mamdo.
Okay, doctor, give me 1 second.
Razin, nanti dulu. Belum. Razin, nanti dulu lah. Chia, you call Razin to... Okay, Mamdo.
Sorry, doctor, I have a problem, so I am opening it from my phone.
So your problems, I let other groups present first.
Oh, okay, okay. Make other groups present first until
Yeah.
Osama come.
Yeah.
Yes, doctor.
Okay, share slide. Group number 17.
So did I share my slide? Okay. Good morning, doctor. We are from group 7. I'm Chakawai and my teammates are Ibrahim and Muhammad Razin.
Ibrahim, bye. On video. Razin, on video.
Oh,
Ibrahim, bye. Mana? Muhammad Ibrahim. Where is your other partner? Muhammad Ibrahim.
not sure way.
Okay, proceed. Proceed.
Okay, so we start from the first question one. And so this question asks us using the block plot methods to design the phase-lee compensator with the starting time of 2 seconds and percentage overshoot of 10%. So the step is, my first step is determine the gain and then the target phase margin. After that, I obtain the gain margin and phase margin from the block plot. After that, I calculate the additional phase. Then from the additional phase, I can determine the value of beta. Then after that, I can, from the block plot, I can get the value of the gain crossover frequency. So with the value of beta and frequency of 10, we can calculate the ZC and PC. So here I calculate the gain from, I assume the ESS is less than 2%. So since this is the unit step response, so is ESS equals to 1/1 plus KP. And then after the calculation, the K is around equivalent to 10. Then after that, get the and from the graph of what is this? Damping ratio over the overshoot percentage, I can get the target damping ratio. And then from the graph of phase margin against the damping ratio, I can get the target phase margin, which is 58.5 degree. So here is the uncompensated block plot. So from the block plot, we can get the original gain margin and phase margin, which the frequency cuts at the 0 dB is the phase margin, and then the phase which cut at the 180 is the gain margin here.
Okay.
So after calculation, the phase margin is around negative 34 degree and gain margin is 18 dB. Okay. So we calculate the additional phase. So here is 100.2 degree. Then by using formula, we can get the beta of 0.012. So from the beta, we can get the maximum magnitude of the lead compensator, which is
Phase lead compensator.
lead compensator. So we can get the magnitude of 19.208 dB. Here. Then from the block plot is around at 20 radian per second, which is around here.
Sure.
Okay, so then we calculate the value of ZC and PC. After that, we can get the lead compensator GC, which is equal to 83.333 times S plus 2.191 divided by S plus 182.584. This 33.333 is 1 over beta.
This is your handwriting.
This I type using Google Doc and then I screenshot.
You tak type. You
So I must handwriting.
bukan. This one is you type ke atau
Type.
you type? Oh, you type bukan copy paste
No. I type.
Razin? Razin, kau dengar tak aku cakap?
Ya, dengar.
Ah.
Type je.
Type
He type in the word Microsoft and we paste in.
Okay. New to me lah, very nice. Okay. Continue.
Okay. So, what is this? So now it's process to using MATLAB to prove my answer. So in MATLAB, I also plot the graph of percentage overshoot against the damping ratio and then the phase margin against the damping ratio graph. So from the graph, the damping ratio and the phase margin is almost equivalent what I found from the graph from Excel.
Same.
Yes, here is phase margin 58.5 and damping ratio of 0.59. What I get from the Excel is the same.
Okay.
So from the block plot, yes, I can, by using the block plot on the MATLAB, I get the phase margin and gain margin. Then put the value that get from the MATLAB and then calculate until I get this value.
Why plus 34?
Oh, here, the phase margin is
Minus 34. Minus.
minus. Oh, yeah,
Minus, minus become plus. Ah.
yeah.
Okay. Betul? Razin, betul tak?
Betul lah tu.
Kau kat mana ah? Yang sayup-sayup.
Bilik tu tu.
Okay, continue.
Okay. So here is the graph of uncompensated and compensated transfer function. So the orange one here is the uncompensated, and then compensated is this line. Because the value of my manual calculation and the value from MATLAB is almost the same, so it's quite near.
Okay, okay.
So I can see it. Is this is here? It's almost the same. So okay, here the come with the second section of the question is we need to plot the time response of 10. Okay, step response of 10. So the first graph is the uncompensated system, and then the middle one is the compensated system using manual calculation, and then the third one is the compensated using the MATLAB calculation. So from the bottom two graph, we can see that the transient time is almost at 2 seconds, and then the overshoot is 67%. Discussion. So from this question, it seems that the transfer function is successfully reduced to 2 seconds, but not sure why the overshoot is not reached the target, which is 20% overshoot.
Okay.
Okay. But from the prop plot, using the lead compensator, we can see that the bandwidth of the compensator is larger than the uncompensated. And then
Okay, finish.
I think finish for the first question.
All right. Next.
Okay, next.
Be quick.
Oh,
Next
the
is
Razin.
yes.
okay, the present.
So Razin, do you want to share your slide or just continue my slide?
You want to present?
No. I mean, this is your present part. So the slide I continue square screen or
Okay,
square.
okay.
You cakap je, dia control.
Okay, for the question 10.6 is about the lag compensator, which is we need to design a lag compensator using the root locus to meet the following specification. The first specification is steady state error must be less than 10% for the step input, and the second specification is phase margin must be greater than 45 degree, and the last specification is settling time which 2% criterion of the time settling less than or equal to 5 for the step input. So we need to design a phase lag compensator utilizing the root locus method to meet the design specification. And next, we need to set a M file script to exist in the design process. Then we test the controller development in part 1A. And lastly, we provide a time history of the output to compute the phase margin using the margin function. To solve this question, we create the solution step, which is first is determine the damping ratio from the required phase margin of percentage overshoot given, and then we obtain the gain from the loop locus. Next, we calculate the final gain and phase from the required steady state error. Next, calculate the ratio of the gain and compare the ZC and PC. Last but not least is choose the value of ZC and calculate the PC by using the gain ratio. And lastly, we check the settling time and other requested parameter of the transfer function in time domain. So this is flowchart for solve the question. Next. To solve this question, we can use the graphical method, which is we can directly get the value for the damping ratio and the percentage overshoot. From the slide, we can see that from the graph we can get damping ratio equal to 0.42 when from the given phase margin equal to 45 degree. And for the percentage overshoot, we will get the 23%. Next. For the manual calculation, we substitute the value of the percentage overshoot equal to 23%, and we will get the same value like using the graphical method. And then we substitute the value for the damping ratio in the formula of relation between the phase margin and damping ratio, and we will get the phase margin equal to 44.96. And then we composite the phase margin and then we will get the 60 degree. And for the frequency, we will get the 1.9047 to run the coding. Okay, for the steady state, in the question is stated that steady state must be less than 10%. And we calculate using the formula of steady state error type 0, which is steady state error equal to 1/1 plus Kp, which is we will get the value for the Kp equal to 9. And the Kp is equal to the Kp compensator, which is the Kp compensator must be greater than 10, greater than 9. So we choose the value for the Kp compensator equal to 10 to include to inside the MATLAB code. For the Kp uncompensator, we will get from the locus, and we will get the value is 5.18 when the damping ratio equal to 0.42. So we can calculate the ratio for the compensator, and we will get the 1.737. So from the locus, we can assume the value for the ZC to create the equation for the compensator. So we must assume the ZC equal to 0.5 because the first pole is near to the origin. And then we will get, we substitute into the ratio equation, and we will get the value for the PC. And then we can create the compensator equation, which is GC equal to 10 S plus 0.5 over S plus 0.2879. Okay, this is our MATLAB code to create the root locus for the uncompensated. And we will get the root locus like this, and we will get the pool is same, not same, is slightly different lah, slightly same with our calculation. And we prove the damping ratio damping ratio from the root locus, and we try to proof, and we will get the damping ratio when the damping ratio equal to 0.42, and we will get the percentage overshoot equal to 23%. And this are the MATLAB code for the when we put the lag compensator in the MATLAB code. And we will get the root locus. Next, to find the phase margin compensator root locus, we create the new, not new lah, new codes to get the phase margin compensator, and from the MATLAB code we will get the value for the phase margin equal to 62.3084. It is similar, not similar, it's slightly different from the manual calculation. And this we prove the steady state error, and we will get the steady state error equal to 0.9 from the MATLAB code, and it is less than 10%. It shows that it's follow our specification that given in the question, and the setting time equal to 2.75 second, which is less than 5 seconds, following the needed specification. And this is the plot from the MATLAB code, and we will get the phase margin equal to 62.3 degree at frequency 13.7 radian per second. Okay. For discussion, a lag compensator can improving the stability and performance. It enhances stability by reducing oscillation and preventing system failure. From the assignment, we can see that the compensator increase the damping, oscillation behavior, and improving the transient function. Cycling time is also improved, allowing the system to reach the desired value more quickly. Like compensator increase the phase margin and gain margin, and reducing the risk of instability and making the system more stable. However, the need for the compensator depends on the specification system, characteristic, and performance required.
Razin, macam pembaca berita. Elaborate je, ringkas, jangan baca. Okay. Ibrahim, bye. Quick, Ibrahim, bye.
Assalamualaikum, doctor. Can you hear me, doctor?
Yeah.
Actually, how long did you share at the first minute when I entered? I couldn't hear anything, not any screen. Razin, until which part you presented, I sent a picture in the group. There was a blank screen when I first joined. When I rejoined, there was. Okay.
Ibrahim, quick.
Connect.
So I present the code now.
Conclusion.
Yeah.
Kakawai can present the conclusion because the Ibrahim is connecting.
Ibrahim, you present later because your internet line is very bad. Where are you?
Doctor, I'm in the campus. Our classroom BT7.
Ah. So what's the problem? Can you present now? Because we are late of time now.
Yes. Hopefully I can. Yes, doctor.
Sure.
Find it?
So, Doctor, here is our first coding for
I can't
the
see. I can't see. Brazil, go.
Can you see my screen, Doctor?
Okay.
So, Doctor, this is our
This one is this is your
this one.
okay. From
This is our
this is your slide.
yes, Doctor. Our group's slide is this.
Slide page.
Slide page 20.
Okay, quick.
Okay, Doctor. So this is our code for original uncompensated transfer function for like compensator, and for now here it is the numerator 110 for the from the transfer function, and now this is denominator of the s square plus 2s plus 20, and for the transfer function we'll multiply here to find out the system transfer function. And now after that from the manual calculation we got zeta. So we plot zeta equal to 0.42 and omega n equal to we got from calculation is 1.9047. So when we plot the root locus here at our gain is again we got 0.01 and overshoot is 48.5%. At when we go down the gain becomes zero. Gain becomes zero, and damping ratio remains the same, but overshoot has a slight increase. And this is the code for second coding for our compensated root locus. And here also we have did the same according to the numerator and the denominator, and multiplied the transfer function to find the numerator second numerator for finding the transfer function from transfer function from open loop closed loop system and here we also use the zeta and omega and value of the same. And finally when we plot the graph, this is also remains the same. The root locus damping ratio and the overshoot also remains the same as the previous one. And there is also no at the both part there is no changes in the frequency response also, so it remains same 4.47. And this is the code to find from question C to find phase margin using the margin. So we just here use everything remains the same as the previous code. We just say plot the phase magnitude, and phase margin and omega to find the board plot and the unit step response. And here using the CISO tool, system input and our system output tool, to plot the phase margin and the step response also. So here we got steady state error is 0.9 as given in the question, should be less than 10%. It remains 0.9. And according when we plot the graph, the settling time is 1.88 per second, which is less than given 5 seconds from the question. And from the when we plot the board plot, here we find that phase margin is 62.3 degree at frequency of 13.7 radian per second. Another thing is, doctor, when we plot it, the phase magnitude, phase margin we didn't get through the 180 degree, and we only have limitation until -135.
Okay, thank you very much. Okay, group 17 can quit. We give way to group 16.
You rather.
Thank you,
Okay,
doctor.
Brembai quit. Razin quit. Group 16.
Hello, Doctor. Assalamualaikum.
Lambat anda eh.
No, Doctor, we already submit, but we key in the wrong group number.
Ha?
We key in the wrong group number.
Buat apa?
Kita orang tulis 14, not 16.
Jadi yang 14 dah belum hantar.
I don't know, Doctor.
Aduh.
Sorry,
Okay.
Doctor, for the
Quick.
convenience. Okay, so wait, Doctor.
Tapi doktor sudah email baru, doktor dah crackkan group number punya nombor. Saya tak perasan semalam. Sorry ya doktor.
16 maknanya dia tak lewat 14 lah. Tapi dalam tu group 14 M5 tu apa? Group 16 lah.
Wait, Doctor. We going to share this slide. And then we are ready to present the assignment. Okay. Yeah, Assalamualaikum, Doctor, and very good morning. Okay, so we are from Group 16, and I am Haziq Faris bin Salazmin, and my partner is Muhammad Asif bin Hamidin. So we are only two from our group. So our assignment question is number 4. So this is our question. So the first question, we need to show that the phase margin is 60 and the percent overshoot to unit step input is 8.8% based on the specification given. So for the second question, we need to obtain a board plot and verify that the design specification is satisfied based on the specification given on the transfer function and the phase margin, which is 40 degree. And the third question, we need to design a compensator based on the specification given on the transfer function and verify that the setting time requirement has been satisfied and the steady state error is 0. Okay, so for the first question, okay, this is manual solution for question CP10.1. So to determine the question, we need to determine the function and the GCS first to have the new transfer function. So to get the new transfer function, we just times the GS and GCS. And then from that things, we can obtain the new transfer function. So to obtain phase margin, To obtain the 8.8% percentage overshoot, we use the 60 degree phase margin. So we use the standard graph for our manual solution to get the 8.8%. So after we use the standard graph, we got exactly the 8.5 range to 9. 8.5 to 9. Okay, so from here, we can see that our calculation is can be proven right. Okay, so this is our graph that we can see, which obtain the phase margin 60 degree, and then after that we can find the percentage overshoot. Okay, next. Okay, I pass to Hasif to present.
Okay, for the second question, the desired phase margin is 40 degree. So in order to get the phase margin 40 degree, we need to calculate basically the value, the formula is x minus negative 180 equals to 40 degree, the phase margin. So the x we get negative 140, and then from the x we use the board plot, which is we assume without the proportional controller. So on the left side, so we get the omega phase margin is 11.5. So from there, we use the magnitude board plot and with the same frequency, and we get the magnitude is 15.4. So from there, we can calculate the gain, which is from the formula 20 log k equals to magnitude that we get, and we get the value of k is 5.89. So from there, we use the value of gain that we get and create a board plot, the new block plot with the gain, and on the right side, we can see that we can get the desired phase margin by by analyzing the board plot, which is on the right side. You can see we track the zero until the graph, and we get the frequency and apply it to the phase graph. So the phase margin that we get is 40 degree.
Dah? Hello, dah?
Okay. No. We continue to the question 3. So we continue to the question 3. So for the question 3, we have a hard time to solve the question, to be honest. So we just do on our own calculation. So hopefully it satisfy you, Doctor. So for the pardon, Doctor?
Last minute.
Oh yeah. So for the calculation for the question 3, we need to have the closed loop pole question for desired setting time is 5 seconds, and the criterion is 2%. So hence we choose the dominant pole, which is we choose for the setting time 5 seconds. So we choose the dominant pole. Dominant pole is TS equal to 4 seconds, which the pole location is S equal to -4. So we just decide the compensator is KS equal to KI over S, and then at S equal to -4, just we got the KI over S plus 4. So by analyzing the closed loop system, we already get the specification GS equal to 1 over S times by S plus 2, and then KS equal to KI S plus 4, based on the compensator that we already calculated before. So after we got all the things that we need, we just transfer to the TS equal to GS times by KS, and then we got the KI over S times by S plus 2 times by S plus 4. already stated in the slide. Okay. So after that, we need to find the K. So basically, we need also to find the steady state error equal to 0. So we need to set the large value of K. For this solution, we just assume that the K is 100 because we need to find the ESS equal to 0. So after we try an error, I think the perfect value is K equal to 0. K equal to 100. Okay, sorry. Okay, and then we just got that Ks equal to 100 over S plus 4. And then finally we got the Ts equal to 100 over S times by S plus 2 times by S plus 4. So next. So this is flowchart for our first question. So we just start and then define which already given in the question, and then calculate the GS and GCS, calculate the phase margin in given 60. And then after that, we need to solve the question, and then using the given 60%, 60 degree phase margin, we can get the PM based on the equation. So we use a standard graph to find the percentage overshoot, 8.8%, and then N for flowchart. Question 1. Next.
Okay, this is the flowchart for question 2. At first, we need to define the transfer function, which is 24.2k over s squared plus 8s plus 24.2, and then we need to calculate the x when phase margin is equal to 40, and then after that we need to plot the dot plot for k equals to 1, which is basically this is before applying the proportional controller to find the omega PM for when phase margin is equal to 40 degree, and then we need to find the magnitude for omega PM and calculate the value for k from the equation 20 log k equals to the magnitude that we get, and then we need to plot the new dot plot using the k obtained and verify the phase margin from the new dot plot that we get. And so that's all for flowchart question 2. Wait. And this is the flowchart for question 3. At first we need to get the desired pole location, which we assume that it is -4, and then after that we need to design the capacitor, and lastly we need to find the value of k, which is we do an assumption, which is the value of k is 100. Okay, this is the MATLAB source code for question 1 and question 2. Basically the step info here in the question 1 is to verify our percentage overshoot in the MATLAB. Either it is 8.8% or not. So the others is the same. So here I assume I put k for the question 2, I put k equals to 1, which is before the proportional controller is applied in the system, and I just put percent k equals to 5.89. This one is I calculated the k, so basically it is not included in this MATLAB code. And then after that, same for the question 2, I just put percent k equals to 1, which is this is not included in the MATLAB code for question 2. And last one, MATLAB source code for question 3. So this is the k is the transfer function g, and then t equals to g over 1 over 1 plus g is to get the closed loop transfer function. And seesaw tool for here we used to plot the graph that we need. So this is the MATLAB result for question 1. So we can see here the phase degree is -120, and after we calculate the phase margin we get 60 degree.
Saya dah baca you punya slide ni, terlalu ringkas, tidak ada Excel file. Satu, kemudian tak ada Simulink. I don't know why. So that is my comment lah.
Nak kena plot plot ni dalam ni doktor, Excel file.
Tadi kau tak baca format ni.
Baca. Okay.
So, saya akan beri markah berdasarkan kepada ni sajalah. Jadi kamu tengoklah nanti kamu punya assignment yang marks. Okay. I think is too brief juga lah, tak banyak sangat, macam last minute work lah. It looks to me like last minute work. never mind. You just look at your marks. If you satisfied, kita nak repair. Kita ikut apa yang ada. Kalau you nak improve, you can tell me. You can ask me. Right. Okay, you can quit now. Kita bagi laluan kepada group number 15.
Okay, thank you.
Okay, thank you, Doctor.
Okay, group 15.
Hi, Doctor.
Sorry for the delay.
Hi, Prof.
Okay, silakan.
Wait. Okay.
Sudah makan?
Belum, 还没吃。
Puasa? Tak puasa. Okay. So presentation jangan baca, elaborate. Kalau baca macam pembaca berita markah rendah. Silakan.
Okay, so good morning, Prof. So we are from group 5. So this is our member. You can see Brian Chong Ting Ong, and me, Chen Kawai, and Godzisin. So we are doing for the assignment for question number 7. So question number 7, there's 3 parts, and this one is the first question, which is CP 7.7. And the question as below: consider feedback control system in figures CP 7.7. We have 3 potential controllers for our system. GC equal to K over S, and K bracket 1 plus 1 over S. So means that the first one is a proportional controller, the second is integral controller, and the third one is the combination of P and I. So it's a PI controller. And the design specification have 2, which is the TS less than equal than 10 second, and PO less than and equal to 10. So this is the figure of the system. So basically we are just changing of the controller here, and the process is still remain the same. So there are like 5 questions in this question. So for the first one, we need to develop an NFL of the K from 0 to infinity and determine the value of K so that the design specification are satisfied. So the design specification means the above these 2. And for part B, we need to repeat the same thing, but this time use the integral controller, and the third time is use the PI controller. And for question D, we need to call plot all ABC in terms of transient response, which is the unit step response for the closed loop system. And for E, we need to compare and contrast these 3 controllers obtained in part A until C. Okay, so next, this is a flow chart of how we do for the question 1. So we begin with plotting the root locus and determine the data value. After then, we find the range of the real axis, calculate the range of K, check with MATLAB, and check if K is valid with the calculation. If it's not valid, then we need to debug again. If it's valid, we need to check until all 3 controllers are done. If not done, we do this again. So if let's say 3 controllers are done, we'll continue with the plot all graph in transient graph and then compare the transient graph. So next. So for the first question, we are doing for the P controller. And then this is a MATLAB code. Because we cannot draw the root locus by our hand, we need to plot it in the MATLAB. So the manual solution is also same as the MATLAB. We need to plot it. So you can see this P, and then the pre-controller is this. So next, this is what we plot from the MATLAB. Next, there's 2 specifications, right? Then the first one is OS is less than equal than 10%. So when we draw this, we can find that the zeta is around 0.591. And if if OS is less than or equal to 10%, the zeta must greater or equal than 0.591. And then the data is less than equal to 53.77. So from the second condition is that the TS value. So when we work on this, TS is less than equal than 10. After we work on this, we get that the real value must greater than 0.4.
Data tu
So,
phase margin
X-axis.
Theta.
Theta is here.
Theta tu face
Theta
margin.
tu, bukan. Theta for root locus.
Apa itu theta?
Theta line.
Yeah, I'm asking Miss Chen individual question.
Oh,
What is theta, Miss Chen?
theta. Zeta line.
What is theta? Miss Go, theta apa?
Theta omega.
Miss Go.
I think theta line.
Huh?
Theta means cos theta will equal to the damping ratio. So
The name of theta.
the name of theta.
What is theta? Saya kena jawab lah.
Cosine of zeta.
Angle of damping ratio line.
I mean cos of zeta.
Angle of damping ratio line. Okay. Terus.
Okay, so let's look from the graph. So this one is from the last graph. So the first condition is that it's 57.7 and below. So when we draw this line, we can know that only the blue line here until here is concluded. And then the second ratio is that 0.4. So you can see from 0.4, there's no line. So it means that every point in here is valid. So from our calculation, we take the point, the maximum point here, and we sub it in our equation. We can find that K is lesser than 11.9496. So that's mean that the K is either is greater than 0 and less than equal to 11.9496. So this is a manual solution. And then for the MATLAB solution, it's basically the same. But for this time, we only take the point. We slide through the mouse, we'll find that the point here is 11.9. So means that this one is the Excel plot, so it's the same thing. So means that the K is greater than 0 and less than equal to 11.9. So yeah. So let's look for part B. So this time we are doing with the integral solution. So this one is a MATLAB code. So what we draw is something like this. And same again, we have the two conditions. This one is the first one. The first is same as the part A. We get zeta less than equal to 53.77. And this is the condition. And then for our second condition, we have the real axis is greater than 0.4. When we look back here, we can find that the maximum here is already over with the 0.4. So means that we can take this directly. And then this is how we calculate the K. So the K equal to Z, this one is the maximum. And then the minimum because of 0.4, the limit of 0.4. And what we get is 1.664. So when we plug all in, it's become K is greater or equal than 1.664 and less than equal to 4.45. So for the MATLAB solution, it's the same, but this time we only scroll through the mouse. And this is the Excel plot. And what we get from here is 4.44 and 1.67. So means that this is a conclusion for 1.67 K until 4.44. Now for the part C, which is using the integral controller, the MATLAB plot is shown as below. And this is the same thing, which is the first condition. And then the second condition of 0.4. So this time, when 553.77 is drawn, you can see that there's a limit from here. And then since the 0.4 is at something here, so means that this equation has been cut into half. And then the gain from here is 0, here is infinity. So that's mean the limit, there's a limit here. And we plug in through the equation, we can find that the limit is 2.77, which is 2.77 until the maximum of 10.04. 9, yeah. So next, when we do with the MATLAB solution, this is the Excel graph.
Okay.
And this time, yes,
Uh,
we are using the mouse to check. Then the mouse show here is, the point show here is 2.77 and until the maximum of 10. So this one is our conclusion for the MATLAB. Okay.
Question.
So we fit.
How you plot root locus using Excel? How you get the data?
I plot it one by one. I take the result of every point, then I put it in.
How you get the data?
Yeah. I use the mouse and click every point, and then I key inside the Excel.
Good. Is there any way from the MATLAB code you can get the data?
For Simulink, yes, but for MATLAB, no.
It's not smart lah. The way you collect the data not smart lah. Okay, nak tengok tu program tu. How you get the data from the MATLAB and then how you transfer to Excel. The program. Brian, can you do it?
Yes. You mean for the Simulink?
Oh, for this Excel, si Miss Chen dia plot daripada MATLAB tu. Macam mana dia dapat data tu? How you get the data and then plot this graph.
I think we all use the same because we find a lot of ways in online. Dia ada others function yang boleh for root locus lah. We can if we plot using MPower, right? We can
data for root locus consists of real and imaginary part. If you go to axis here, the real part, all are real data. If you go to the orange go up and blue go down, you have a real and imaginary part. So how you differentiate that data?
All right. Let
That's
me.
why I asked Miss Chen, tapi dia tak jawab. Dia kata dia ambil satu-satu. Kalau ambil satu-satu sampai pension habis . Okay, can you scan?
But later got a Simulink can use directly. Yeah, okay. So these are root locus. We take one by one.
Okay, be quick.
And then, okay. So next.
Laju sikit.
Okay, laju sikit. Okay, so this one is for the D, where we plot everything together. So you can see every one of it has a range. So we take k equal to 3. So this one is the MATLAB code. And then this is what we draw here. This one is from MATLAB. You can see every of the plot here. And then the one original is the one with no k value. And next, this one is the Simulink. So we basically get the same thing. And then from the Simulink, we can take the data and then plot it in the Excel file. So this one is the solution to get how to get the ESS. So this one is the manual solution. Basically, you just find the KP first, and then you find the ESS. So this one is for the proportional controller, integral controller, and PI controller. So next, we'll look for the rise time, setting time, and also the peak amplitude and the final value. So basically, this one is the same. You just calculate. And then this one is a general for what to compare. So for part E, I compare it with the table. You can find that for integral controller, there's a OS, and proportional controller, there's a steady state error. Okay. So this one is our discussion for question 1. P controller has the quickest rise time and settling time, but has the highest steady state error. I controller and PI controller eliminates the steady state error. I controller has percentage OS. The findings of this is that PI and PI controller is being compared. It's found that every of it has its pros and cons. Thus, it should be used according to its the specification. And PID might have a better choice as the D controller serves the purpose of minimizing the transients error. The combination of PID controller can be used to control magnitude and phase problems. And this is the conclusion for question 1. The effects of applying PI and PI controller has been successfully seen. Okay, next.
Next.
Okay, can you hear me?
Laju.
Okay. So I will in charge of the CP 7.8. Consider the spacecraft. So we need to find the controller is PD controller. So we need to develop an file to find the KD over J and KP over J for this question. And with the settling time of TS is TS smaller than or equal to 4 seconds, and the overshoot is smaller or equal to 10%. And we need to use the 2% criteria to determine the settling time. Next.
Determine, bukan determine.
Okay,
Determine.
basically, this is the determine. Basically, this is the flow chart of the question. So the first we sub the KP over KD into the equation, and then we find the plot at 0 for the system. Next, we plot the root locus at the MATLAB by assuming the damping ratio, the overshoot is 10%. So we find the damping ratio at theta, and then we plot the spread line on the root locus. Next, we find the closed loop pole and natural frequency. Then we calculate the setting time to make sure that the requirement is fulfilled. So if the requirement is not fulfilled, we will do it again by using different overshoot value. And then if the requirement is fulfilled, we calculate again and KD over J and KP over J. Next. This one. So for the equation is KD over S plus KP over JS squared equal to KD plus multiply with S plus KP over KD over JS squared. So KP over KD is 5. So we will sub the 5 into the equation. So we can find the transfer function for it. And then we can know the system type is type 2 and the pole is 0 and the 0 is -5. So we will assume the percentage overshoot is 10% and 0%. Next. Previous slide.
I think you can access control because Kawai has access the control.
Continue.
Oh, wait, I cannot control. So first, the percentage overshoot is 10%. So we find the damping ratio from the percentage overshoot and damping ratio graph. So we can find the damping ratio is equal to 0.591. So the theta is 54 degrees. So from the root locus plot, we can find using the damping ratio equal to 0.591 to find the closed loop pole. The closed loop pole is equal to -3.548 plus 4.76 J. And the natural frequency is 5.89 radian per second. So by using the percentage overshoot is equal to 10%, we find the settling time using the 2% criteria. So the settling time is 1.15, which less than or equal to 4 seconds. So our requirement is fulfilled. So we can find K using the closed loop pole, which sub into the equation, the previous equation, and then we can find K. So I find the K is 6.96. So then we can find KD over J and KP over J. Next, we will assume the percentage of overshoot is equal to 0%. So the damping ratio is 0.977 and the degree is 12 degrees. So 12 degrees we plot in the root locus. So this is the root locus. The closed loop pole is -9.55 and plus 2.06 J. And the natural frequency is 9.77 radian per second. So by using this closed loop pole, we can also determine the settling time by using the 2% criteria. So the settling time is 0.42. So the requirement is also fulfilled. Then we can find the gain by using the formula by sub the closed loop pole in our equation. So we can find the gain and KD over J and KP over J. So we can conclude that the KD over J is in between 6.96 and 19.1. And the KP over J is between 34.8 and 95.5. So this is the MATLAB source code, and the N is equal to the numerator, and the D means the denominator. So we plot the root locus and plot the zeta line. This is the zeta line. And we use S script to plot the zeta line. And then this is the Excel plot of the root locus by you. And then this is the Simulink solution. And then this is the Simulink waveform for the time response of the second order system. And then this is the Excel plot from the Simulink we merged to the Excel. So for the discussion, we can observe that the KD over J is in between 6.96 and 19.1, and the KP over J is in between 34.8 and 95.5. So if we want to increase the value of the gain, means the KD over J and KP over J, we can use a low percentage overshoot. So from the root locus, we drag the mouse, can see when the overshoot decrease, the poles, the closed loop pole will become different. Okay. So when we sub the closed loop pole into the equation, the gain will increase.
Next. Okay.
So conclusion is the specification of the PD controller smaller than 10% and setting time smaller than 4 seconds are achieved. So the value KD over J and KP over J are accepted. Next, I will pass to Brian to present his slide.
All right. So, previous slide. Also consider the feedback control. So you can see this is just a simple feedback system. So we have to find the range of K, and we have to find the value of K in order to get the damping ratio equal to 0.70. Okay. Sorry. Sorry. Okay, so we have to get the angle of the damping line, the zeta line. So it's 45 degrees. And because I don't have the graph, so I just directly use the root locus in the MATLAB to get the dominant poles. So which is negative 0.817 plus minus J 0.818. So in the manual calculation, I sub the dominant poles into the equations to find the gain, which is to times the pole length of all the poles. No, sorry, all the open, to sub the dominant poles into the open loop poles equation, the open loop pole length. So we can find that the K equals to 9.16 from the manual calculation. So this is the flow chart. We have to plot the root locus using M file first. And then we have to add zeta line to the root locus, identify dominant poles, and then get the K using manual calculation. Then we just verify it using MATLAB. Compare the result. If it is not valid, then repeat again. If it is valid, we continue to plot the time response graph using Simulink and Exafloat and Descent. So this is the MATLAB solution. And as you can see, this is the source code, and we use grid to get the grid line and S grid to get the zeta line. So this is the root locus using MATLAB. And then we can find that the open loop post is correct, which is negative 8.2, negative 1.65, and negative 0.148 from the open loop transfer function. And then, So this is the root locus plot with the zeta line, and then we can find the values of the dominant poles where the zeta line intersect to the root locus, which is negative. So we can verify that we can see that the gain is 9.18 at the dominant poles of negative 0.817 plus 0.818 height. So we can see that, okay, this is the root locus plot in Excel plot. All right, so we can see that the solution, the gain K obtained from manual calculation is similar to the MATLAB one. So this is Simulink. So this is the graph plotted using Simulink, and then we transfer the data, we obtain the data from the scope, and then we can plot it using Excel plot. As you can see, right, actually the setting time is quite high, and then there is statistic error. So in the discussion, so I proceed with the gain K first, which is verified already, it is acceptable. And then for the time response graph, you can see that the statistic error can be improved further. And then the transient response, such as this for the setting time, we can also improve further. So we can come up with a short summary that the PID controller can be used to enhance the overall system performance. And for the conclusions, and it's similar to discussion. So it's identical for the gain value, it is acceptable. And then for the time response, we can further enhance by using a PID to minimize the statistic error and to improve the transient response. And that's all from group 15. Yeah,
okay, I have nothing to comment. Very good slides. I want to know, email to me how you transfer from Simulink data to Excel. That's all.
Yeah, we have the files. We have the Excel files included in the zip file.
Oh, in the zip, everything is there. Okay.
Yeah,
so
yeah.
Corresponding person is Brian Chong. Okay, thank you very much. You can exit the Zoom. Group number 14.
Thank you, Prof.
Okay, thank you, Prof.
Thank you, Prof. Thank you, Prof.
Group number 14. Irfan,
Ya, Doktor.
Irfan dengan
Chong Jin Su, Vicky Boon.
Hello, Doctor.
Satu komputer tak boleh share dua orang mah.
Because yesterday my laptop black screen, so now it's under repair. So no choice.
Okay. Proceed.
Yeah, sure.
Irfan Okay, laju sikit.
Okay. Ya.
Jangan,
Assalamualaikum and good morning and good afternoon.
jangan baca slide.
Okay.
Baca
So
slide.
we are from group 14 and we are going to present our assignment which is we are answering question assignment 2. So moving on. So firstly, this is our group members, Vicky Boon, Chan Yi, myself, Muhammad Irfan, and Chong Jin Su. So for the first question, so this question is just a simple one. So consider the feedback system shown in figure CP7.1 where GS equals to S plus 2 over S squared. So for what value of K is zeta equal to 0.707 for the dominant closed loop poles? So we need to solve the problems manually and write the MATLAB code and MPAN to verify our answer. So for the manual calculation, the given transfer function is open loop transfer function. So to solve the question, we start to obtain the closed loop transfer function. And from S plus 2 over S squared, we will get Ks plus 2K over S squared plus Ks plus 2K. So as the closed loop transfer function is now a second order equation, so we compare the characteristic equation with the characteristic equation of the general equation for second order system. So the first parameter we compare is omega n squared with the 2k, and we will get the omega n equals to set 2k, and then the 2 zeta omega n is compared with the k from the closed loop transfer function, and by inserting the damping ratio that is given, which is 0.707, and the omega n from the previous equation that we generate from the comparison, we can solve the k as 4. So for the verification process, we will plot the root locus in the MATLAB. Next, okay, so this is the source code for the MATLAB. First, we give the value for the numerator and denominator and make the transfer function, and we plot the root locus. So for verification, we try to find the damping ratio that is given, because the question wants us to find the gain at the damping ratio. So by shifting the mouse, we get the damping ratio at damping ratio 0.708. We get the gain as 4, which is the same as the manual calculation lah. So we actually this question we can we have export the data from the MATLAB to the Excel file, but I don't really find the suitable function in the MATLAB to plot the data. Like we have the file, the Excel file that collect all the data, but when trying to plot the data, it doesn't give the same root locus, the same plot as the one in the MATLAB. So as for the step response, this is the step response, the source code for the step response, which is the closed loop one with the gain. So we also observe the parameters of the step response through the MATLAB code. And then next is the simulink. The simulink is for the closed loop transfer function with the gain, and we did some comparison with the comparison between the parameters from the simulink and also the MATLAB. So next, okay, so this one is the Excel plot for the step response. We also as can be seen, we have export the data from this transfer function to the Excel, and then for the step response, we can plot the data in the Excel. So next, this is the flowchart for answering question 1. The first one is manual calculation, and then write the MATLAB for verification. And we find we're moving the mouse to find the damping ratio for verification and compare with the calculation. So as we got the value is the same, so we proceed to generate the step response of closed loop system and MATLAB, and we implement it in the simulink before we export the data for plotting in the Excel. So a bit of discussion. So basically, for the discussion, discussion is just I just reiterate the point that I have successfully obtained the gain at damping ratio of 0.707 as with value of gain equals to 4. So, but the MATLAB and Simulink, by observing the parameters, we can see that the response shape are the same, and also most of the parameters are the same, but there are some parameters that are different, which is the settling time and the rise time. So for this, the possible explanation is it can be due to the numerical issue, which is caused by the simulation step size and the Simulink. So the MATLAB will be the more exact one lah, the more accurate one. So in the Simulink, the step response is evaluated in time steps. So if we use the default simulation parameters, these step times could be larger than what is necessary to accurately describe the behavior of the system. So basically the response, the time parameters in the Simulink will be larger than the one in the MATLAB if we use the default system.
Next.
So that's all lah.
Next Q.
That's all for question 1. I pass to my group member for question 2.
Next person.
All right, good afternoon, doctors. Prof. So I'm Vicky Boon. I'm presenting about the questions 2. So for questions 2, we have a large antennas that's as shown in the diagrams, and the system requirement is we want the steady state error for RAM input less than or equal to 0.01 B, where B is the constant for RAM input, and then we want for the percentage of the overshoot to state input is less than 5%, and the settling time is waiting less than 2 seconds. So it's required for us to use the root locus method by creating an M file to assist in the designing of controller. Secondly, plot the unit state response and compute the percentage overshoot and the settling times. And the third one is we determine the effect of the disturbance to the output of the Y. So first of all, we developed a MATLAB course for the original system to observe its original damping ratios and overshoots. So this is the code, and then we observe that at the gain of 10 that is required by the original system, the overshoot is quite large, it's about 9%. And then for the state response, the settling time is around 18.6 seconds. So it has to be improved. So let's do some manual solutions for the part A and B. For first of all, if we want to we wish to reduce the ESS and improve the OS together with the settling times, so it have to use the PID controllers. So the first thing, sorry, need to charge.
Continue.
Sorry. So the first thing we do is we set the settling time is less than 2 seconds. So we set it as 1 second, and the OS percentage is the requirement is 5%. So we set it as 3%. So for 3% of the overshoot, we get the damping ratio is around 0.74, and then we plug into the equations of the settling times. We get it for the new dominant pulse. So it's around -4 plus minus 3.7 J. So the original one is around -1.x and 2.636. So with this dominant pulse, we develop our new PD controllers and by the manual calculations methods, and we get that the new zero is around -0.5 at 2, with the gain of 35.7. But we still need to improve our steady state errors. So we have to add in the PI controller by adding a pole to the origins that it will affect our closed loop poles. So we need to add a zero that is near to the poles. So it's around 0.01. So this is the PID controller together. And then we plug in this PID controller, design the controllers into the original system. And then we made it into the MATLAB. And then we found the gain is around 34.9. So this is the complete system that we developed. So next we have to check for the ESS. For the original ones, it's required for the RAM input. So if we use the KB, and then we found that the ESS is around 5. And then after that, after the improvements, the KB is improved to 0. So we prove that PI controller can eliminate the ESS. Then we check our system by using the MATLAB code. So we observe the root locus first. Then we found that at these damping ratios, the gain is 34.9. So we plug it into the system by this one, 34.9, and we observe its step response. So originally it is this red line with 18.6. After improvement is reduced to 1.12 seconds, and the overshoot is around 4.52, is less than 5. So it's within the range. So next thing we check for the ESS, and then we found that the blue color one, is original closed loop transfer functions with the with the RAM input. The ESS is around 5. That is same as our calculations. After the improvement, and then we found that the ESS is already reduced to 0. This one is the Simulinks. For the Simulink parts, to ease our designs, we just plug this is original one with 10 as GAN and then 1 15 50 0 same as the open loop transfer function, original open loop transfer functions. This one, the origin, sorry, this one. The original open loop transfer functions, and then we compare the answers with the design one, and then we found that, and then we export the data to the Excel and block and then plot in Excel. So this is the Excel plot. The blue line is the original response, and the red line is the improved designs. Designs. And then we can see that the trend is still same as the original one, the original from MATLAB code. And then so we can prove that our design is correct. This is a flow chart for questions 2A and B. So first thing, we create an M file to observe our original response, confirm the specifications, and then do the manual calculations. And then also the manual calculations for the ESS. Then we plug into the MATLAB code and then to observe is it the desired output. If not, then we do some gain adjustment. If yes, then we proceed to the Simulink. And then we export the data to Excel and then plot the data in Excel and observe is the data meet our requirements. If no, then we do some adjustment. And if yes, then this is the end of our questions 2. For the discussion part, for the original system, we have found that the settling time is around 18.6%, overshoot is around 9%, and we have ESS with the rank input around 5. It's quite a huge problem. So we target our overshoot percentage at 3%, and the ESS is 1 second, and then with no steady state errors. So this in order to meet these requirements, we have to use the FUA'AD controllers. So after the improvement, we found that our ESS is less than 5% already. It's around 4.52. The improvement is around 49.7%. For the ESS, we reduce it to 1.12 seconds, and the improvement is around 93.9x. And the ESS is already reduced to 0. The improvement is 100%. And then the Excel and the MATLAB plot has insignificant errors because the trend is still there. We still can observe its response for both originals and improved system. So this is all for the question 2A. Now we're moving for the question.
Continue. Tak nampak. Kamera tak nampak.
Camera?
Part C of question 2.
Nampak hidung ni. Nampak hidung. Tak nampak mata. Continue.
So this is the part C of question 2. We use the same system, but this time we need to determine the effect of disturbance as here. So what is the effect of disturbance TDS on the output YX? So first of all, we use manual calculation for part C. So we assume the input, this part, we assume the RS is 0 first. And then to find YS over TDX. So we redraw the block diagram and simplify it. We can find this one, TDS as the input, and then we calculate it and simplify it. Eventually we'll get YS equal to minus TDS over UCX. So that means to minimize the effect of TDS, we should increase the denominator of GS, the gain of the PID controller, to reduce the effect of the disturber on the output. Later we use Simulink to implement this system. it shows that when the disturbance is added into the system between the PID and the GX, so it will increase the steady state error. The final value will not be the 1, and it will decrease a little bit like this, the blue line. So I export this using MATLAB to the Excel plot. So it's a similar trend. Okay, flowchart for the part C is we should assume the input RS equal to 0, and then to find the transfer function of the YS over TDS, output over the disturbance. And then we implement it on a Simulink, and we export the data to the Excel and plot the stat response. So we can compare the system with and without disturbance. So finally, we analysis and discuss the result. So from the result, I compare with this and the system when we do it. So we can find that the disturbance will increase the system error. So the final value of the system will not approach it when the times go to infinity. To improve this problem, so we should increase the gain of the PID controller. For the conclusion of our project, the gain of the Q1 is found, and then it can be proved by corrected by MATLAB and Simulink. And then the target of improvement of system Q2 has achieved. And then we also analyze the relationship between the disturbance and the output performance. So
Okay.
this is our research.
Question, Ms. Chong.
Yes.
What is the example of real life for disturbance in your system?
Real life of disturbance.
Real life examples. Your system is a antenna control system, right, Vicky?
Yes.
So what is the real sample of disturbance?
I use this as an example. Like this antenna, and then we want to transmit the signal, and then within the antenna it may cause some noise, internal noise inside it. So this is the disturbance.
Internal noise, for example,
thermal noise.
Thermal
noise.
Thermal noise.
Other than that, I think maybe the surroundings environments, like maybe for rain, winds, maybe it's also affect our satellites.
This one is outside of the satellite.
Rain, heavy rain. Strong wind.
Yeah.
Lightning. Irfan?
Yeah, it can be.
Any more example?
Like this is light and it moves.
Tak tahu.
I mean like the signals like must accurately track like the movement of the satellite. So I think the main one would be the natural thing lah, natural things.
Natural tu apa? Contohnya?
Like you stated before lah, like the wind and the rain, something like that lah, the main one. Because it needs to track the movement.
Okay, group 14 can exit. We give way to group 13.
Okay, thank you, Doctor. Thank you, Prof.
Thank you, Prof.
Thank you, Prof.
Group 13 masuk.
Hello.
Okay.
Okay. Can you hear me, Doctor?
Cepat sikit. Jangan
Okay.
baca. Elaborate.
Alright. Okay, Assalamualaikum warahmatullahi wabarakatuh. Today we are from group 13, are going to present our assignment given to us, which is assignment 1. Okay, this is the first question, CP 7.1. Using the root locus function, obtain the root locus for the following transfer function when the gain starts from 0 towards infinity. For question A, the transfer function is 25 over s cubic plus 10s squared plus 40s plus 25. So the flowchart will be applied towards the whole CP 7.1 because there is 4 questions. Firstly, we write the MATLAB code in an M file for the given OLT, for the given open loop transfer function, and then we run the script and it will display the root locus of the open loop transfer function. And then only then we do the manual calculation for the breakaway point, asymptote, and also the JW crossing, and then sketch the root locus. We compare the manual sketching with the MATLAB plot, and then it is similar results. Then we consider that the root locus is validated. And then if it is not the same, we then will recheck the calculation and we check the calculation and also the sketching for error. So for the first question, using the transfer function, we firstly factorize the denominator to acquire the poles. So there is 3 finite poles and no finite zeros. And then using the value, we calculate for the real axis intercept for the asymptote. And then the asymptote real axis intercept is -3.23. And there for the angle, there will be 3 asymptote, meaning there will be 3 angles, 60 degree, 180, and also 300. And then acquiring the characteristic equation from the closed loop transfer function, we did the Roth-Squiz table to acquire the range of K. So, and we found that K is stable only for when K is larger than 0 and less than 15. Using the maximum value of K, we then can gain the JW crossing of the root locus. So this is the manual sketching for the root locus. Next. So using the M file script, firstly, we convert the S as a transfer function variable, and then we define the transfer function. And then using our locus function, MATLAB will then display the root locus plot, and we also enable the grid. As you can see here, the MATLAB root locus plot is similar to the manual sketching, including the JW crossing and the system maximum gain. So for question CP 7.1a, I can say that the result is validated.
Next, for question CP 7.1b, the given open loop transfer function of the system is GS equal to S plus 10 over S squared plus 2S plus 10. The question asks to obtain the root locus by using the R locus function. For manual calculation, we obtain the open loop 0 is -10 and open loop poles are -1 plus J3 and -1 minus J3. In order for us to find the breakpoint of the root locus, we need to differentiate the open loop transfer function and make it equal to 0. So the breakpoint of the root locus is -19.4868. And then to find the corresponding gain K at the breakpoint, just use the formula K equal to 1 over modulus of GH. And then from the root locus sketching, the root locus begin at the finite and infinite poles and end at the finite and infinite 0.
Finite apa? Finite. Infinite. Bahasa apa kau pakai ni? Jawa ke bahasa Jawa? Finite, infinite. Cuba sebut.
Finite, infinite. Here is the MATLAB source code. to generate the root locus. Next, here is the result obtained. So as a conclusion for this question, the sketching of the root locus and the generated root locus from MATLAB is equal. So the result is valid. Next, for question CP 7.1c, the given open loop transfer function of the system is GS equal to S square plus 2S plus 4 over S multiplied by S square plus 5S plus 10. So the question asks to obtain the root locus by using the R locus function. For manual solution,
One salah tu.
Siapa yang masuk tu?
Okay.
User.
For manual solution, we obtain the open loop 0 is -1 plus J 1.73 and -1 minus J 1.73. And the open loop pole are -2.5 plus J 1.94 and -2.5 minus J 1.94 and lastly 0. In order to find the breakpoint, we need to differentiate the open loop transfer function and make it equal to 0. So here there are two breakpoints, which is -1.421 and -2.968. And next, to find the corresponding gain K at the breakpoint, just use the formula K equal to 1 over modulus GH. From the root locus sketching, the root locus begin at finite and infinite poles and ends at the finite and infinite zero. Here is the MATLAB source code to produce the root locus diagram from MATLAB. And then this is the diagram of root locus generated by MATLAB. So the sketching of the root locus from manual solution and from MATLAB is same. So the result is valid.
And then for question CP 7.1D, we are given the question open loop root locus, which is when we see the poles is S power of 5 and the as the 0 is S of power of 5 and the poles is S power of 6. We need to using the MATLAB equation, we need to do transfer function and then the value of K is from 0 to infinity. Then we use manual calculation, we get the open loop zeros, which is we get 5 open loop zeros, -5.2568, -0.3086 plus minus J 0.9387, and then the last one is -0.063 plus minus J 1.2281. And then for
no need to read lah. You just mention open loop zeros, open loop poles. Kan dah cakap, jangan jadi pembaca berita. Ringkas je. Kalau tak nanti lambat habis.
And then for open loop poles, we get 6 open loop poles. And then for this function, we cannot get the breakpoint because when we differentiate the equation, open loop transfer function, we get the root locus of S power of 10. And then we cannot find the breakpoint. And then again, also we cannot solve. And then we number of asymptote, we get 1. And then real intercept, we got 2. And then angle for this transfer function is 180 and 540. Next, for MATLAB source code, this is the MATLAB source code for this transfer function. And then for the result for root locus, this is the result. We can see we get 5 zeros and then 6 posts in the root locus. And then for discussion part, you can see when observation is higher order of transfer function for function are generally more complex and harder to analyze compared to lower order because we cannot solve the equation for finding the breakpoint. And then for finding, we get the system that have finite number of zeros for the left half plane tends to be more stable compared to the zeros at the right half plane. And then for the suggestion, we consider the model reduction technique to reduce the number of order of the function, and we need to explore advanced control technique suitable for higher order system. And then for improvement, we need to adding zeros in the left half plane. We shift the root locus direction in the other region. That will making the root locus more stable.
Next, for question CP 7.2, the given open loop transfer function of a unity negative feedback system is KGS equal to K S square minus 2S plus 2 over S multiplied by S square plus 3S plus 2. So the question is to plot root locus via MATLAB and also use the rlog5 function to show the max value of K to be stable. From the manual calculation, we use row Hurwitz table to find the J omega crossing. This J omega crossing point separate the stable and unstable operation. So the first step is to find the characteristic equation from the closed loop transfer function. Then find the gain K at a row of 0 and forming the polynomial with K equal to 0.7191. So hence the range of stability is K greater than 0 and less than 0.791. Here is the flowchart to explain each step of the solution. So write the MATLAB code for the given open loop transfer function, display the root locus, and then using the rlog find, we can also find the K critical at J omega crossing, then do the manual calculation, and then compare the result we obtain from manual calculation with the root locus from MATLAB. Here is the MATLAB code source. And this is the result obtained. So lastly, we managed to find K using our log5 function as shown in the slide. So I can conclude that the K critical from manual calculation is same with the K critical from MATLAB.
Izul, mana Excel file?
Excel file.
Excel file.
Tak buat, Doktor.
Astaghfirullahalazim. Kan dalam format tu dia ada cakap. Tidur ke kau orang ni? Excel file. Siapa ketua kumpulan? Okey, teruskan.
Discussion. Okay, so from the observation, the value of K that we get by using our log find is not precise because we cannot precisely select the J omega crossing from the MATLAB. So if the K value is greater than 0.791, the system becomes unstable due to the root locus is on the right half plane. So RH criterion state any system can stable if all the root of the first column have the same sign. Means that there is no sign change in the first column of RH table. So the exact of K value can be found from manual calculation, which is from RH table, and the design of system need to consider always in other than region so that it becomes stable.
For CP 7.1 and 7.4, we are given unity negative feedback system, which is root locus GC S equal to GS And then we need to develop M file to obtain the root locus as P varies from 0 to infinity. And then we need to find the P for closed loop pool, which is stable. And this is for manual calculation. First of all, we find the characteristic equation. We use 1 plus GCS, GS equal to 0. And then we recalculate. And then we get the function 1 plus PS minus 1 over S squared plus 5S plus 10 equal to 0. And this is the open loop transfer function. And then from open loop transfer function, we do closed loop transfer function to find the characteristic equation to RH table. And then from RH table, we can get the range of stability for closed loop poles, for closed loop, which is 10 minus P must be greater than 0. And then we calculate, we get the P must be less than 0. And then for the range of stability we get for closed loop is from 0 to 10. And then this is the flowchart for this equation. First of all, we find the characteristic equation, and then we determine the range of P for stability closed loop. And then we write the MATLAB code using M function, and then we display the root locus, and then we compare the value for P in MATLAB plot using manual calculation and in MATLAB. When the result is similar from manual calculation and MATLAB, we end, and then when the root locus is not same, we recheck the manual calculation to find the value of P. Then this is the MATLAB source code. And then this is the result for MATLAB. What we see is, we can see the gain is follow the closed loop stability, which is from 0 to 10 gain. Then for discussion, we can observe the value of stability of closed loop in MATLAB is similar with manual calculation, which is between 0 to 10. And then for finding, we get the P value cannot be exceed more than 10 because when the root locus at the right half plane will be unstable. And then RH table can be used to calculate the range of stability. And then for suggestion, we must make sure all the poles are located within the left half plane of the complete plane. And then for improvement, this question is we need to consider adding gain limit to prevent excessive amplification to the right half plane.
So for the last question, which is CP 7.10, we are given system represented in state variable form. So we are given the state space equation, and then the question asks us to determine the characteristic equation, find the value of K for when the system is stable, and then develop an M file to plot the root locus. Next. So this is how we solve this problem. First, we determine the characteristic equation from the given state space function, and then finding the range of K using RH table, and then write a MATLAB code in the M file to plot the root locus, run the file, and then it will display the root locus, compare the manually calculated K with MATLAB plot, and then if it is similar, then the objective is completed, and then if it is not, then we have to recheck the manual calculation for error. So this is the manual calculation. Firstly, as you can see here, all the matrix, all the state space equation is here. And then by multiplying S with identity matrix, we acquire SI. And then to find the characteristic equation, we find the determinant of SI minus A. And then we got S cubed plus 2 plus K S square plus 5S plus 1 using the RH table.
SI though.
SI?
What SI?
SI, S times with identity matrix.
Oh.
Okay. Okay. And then for when we are finding the range of K, we see that K must be greater than -1.8 and also K must be greater than -2. So we conclude that the system stays stable for any value of k equals to 0. K more than greater than 0. So there is two version at that time. There is two version of this of the answer, which is the first one is that when we solve the state space equation, we then can acquire the first GS, the upper GS here, the transfer function. And then I just realized just now how we can end up with the second answer. So jalan, so this is the sketching for both transfer function. The first one have zeros at the right half plane of the S-plane. So only looking at the sketching, we can see that the system will become unstable as the gain increase to infinity. But for the second one, we can see that the direction of root locus will end at both zeros at origin and then one infinite zeros at the left half plane. So this is the MATLAB results for the first transfer function. As you can see, the sketching differs with the MATLAB results due to not taking account the departure and arrival angle. Next. And then this is the MATLAB result for the second transfer function, where there is 3 poles, 2 zeros, and 1 infinite zeros. Next. So the observation is in version 1, the root locus did not satisfy, in version 1, as we can see just now, the root locus did not satisfy the range of k that we acquire, because as the k increase, the system with the root locus will move to the direction of the right half plane, which make it unstable, while version 2 satisfies the stability range. Both versions have 3 finite poles and 2 finite zeros. Our findings is that in version 2, the critical k value is 0.101. And then some suggestions for this question is that rather than sketching it, it is better to use plotting software. Near to the origins, the direction of the root locus will not shift to the right half plane and making the system unstable.
Okay. Again?
So for the conclusion, we conclude that root locus method are also a reliable method to analyze the stability of a system other than frequency response analysis that uses magnitude and phase board plotting. A reliable system is that of root locus system will be in the left half plane of the S-plane, which is under damped region as the gain reaches infinity. Other than that, we can analyze the absolute stability of the system. We can find the limiting value of the system gain k for any point of the root locus, and this will enhances system designing with better accuracy. The maximum k for the system to be stable is on the JW crossing axis, which is known as k critical, and it can be found using characteristic equation from the closed loop transfer function, and then proceed with the RH table. In the end, we managed to complete the assignment. We gain a lot of knowledge in using MATLAB along with doing revision in preparation for the upcoming final exam. We would like to wish many thanks and appreciation for our lecturer, Prof. Dr. FUA'AD Rahmat, for his guidance and teachings.
Jahid ke boleh apply lah TV3 Astro Awani.
Sorry, Doctor. Conclusion macam kena baca.
Elaborate. Buat apa baca? Kan dah cakap tadi. Elaborate. Cuba sebut.
Elaborate.
Dah, okay. Thank you very much. So tak ada Excel Simulink pun tak nampak.
Oh, kita hanya guna M file je.
Dalam tu ada Excel file dengan Simulink. Tak ada Simulink Dah, makan.
Boleh baiki lagi ke?
Boleh, tapi submit lagi satu lah. Ada moment markah rendah lah sebab requirement dia ada Excel file dengan Simulink file. Awak main M file je. Format tak ikut dia. Format. Tak baca ke format?
Baca.
Okay. So baiki dan submit lagi Sabtu, tak perlu present lah. Kalau ada, saya bagilah. Kalau tak ada, status quo macam markah sekarang.
Okay, baik.
Alright, thank you.
Alright, thank you, Doctor.
Welcome.